A warm welcome to all of you students, those who are watching this video. My name is 𝐈𝐧𝐭𝐫𝐨𝐝 and I am the creator of this community called the Era of Chaos. So today's video lectures is all about based on the gamma functions. Actually, I am going to start a new series of problem solving and theoretical approaches of solving problems based on some special kind of integrals, special kind of functions. So basically today's session is based on the gamma functions. So as it is based on gamma functions, so without delaying I am going to write the functions called the gamma functions or the gamma integral. So this is the the so the gamma function is basically defined as this is the gamma sign. Okay, so this is the gamma sign and this gamma function is written as the gamma of n 0 to infinity, okay, e to the power minus x, x to the power n minus 1 dx, where the n is a positive number. So this is the way to represent the gamma functions, or this is the setup of gamma functions. So while you learn the integration, you will work with two main types of integral. So one is definite integral and indefinite integrals. Okay, so the difference between the two is those definite integrals have limit of integrations and indefinite integrals do not have the limits. I mean, when you first start working with definite integrals, you will use simple real numbers for your limits of integration, but we'll soon see that more is possible. It is very common to see upper limits of integration set to infinity and lower limit set is negative infinity. So any definite integrals that has one or more infinite limits of integrations, or an integrand that approaches infinity within its limits of integration, is known as the improper integral. So what is the necessity of improper integral? The purpose of using improper integrals is that one is often able to compute values of improper integrals even when the function is not integrable in the conventional sense. Okay, so because of singularity in the function as an integrand, or because one of the bounds of integration is infinite. So first deriving this gamma functions, or how to evaluate these gamma functions, we'll first see that the convergence of this gamma integral, or how to perform the convergence to check that whether this gamma function is convergent or not. So we'll start by claiming that this is the setup of gamma function. So let me highlight it. Yeah. So this is the setup of gamma function. The setup. Okay. So this is the setup of gamma function. So next is the convergence of gamma integral. So convergence of gamma integral so as it is already claimed that a gamma integral is an improper integral, so before going to compute this integral we need to check whether this improper integral is convergent or not. so here the function is x to the power n minus 1 e to the power minus x. So we write the given integral as, so we write the given integral as, so as it is so 0 to infinity, okay sorry maybe I'm sorry, bit of length of this page is getting problem. So as so 0 to infinity x to the power n minus 1 e to the power minus x dx is equals to 0 to 1, okay, x to the power n minus 1 e to the power minus x dx, okay, and 0 to 1, sorry, it would be 0 to infinity, 0 to infinity x to the power n minus 1 e to the power okay, so e to the power minus x dx, right? So we considered the two integrals separately. So first consider the 0 to infinity one. So when n minus n is greater than 1, so this is a proper integral. So this integral, so this is so this integral is proper integral, and you know that. So as this integral is proper integral, so hence it is convergent, right? But the question is solving with this integral, okay? So when, so let me write so when m is less than 1, the integrand is unbounded at x equals to 0, right? The integrand is unbounded at x equals to 0, okay? Then we have then we have the limit x minus 0 to the power mu of f of x. So limit is x tending to, so 0 plus 0, that means positive things I am taking, 0 plus 0. Okay, now this limit x 0 plus 0 x1 minus n and x to the power n minus 1 e to the power minus x, which is 1, right? So which is a finite and non-zero limit, right? So the integral will be convergent, so integral will be convergent when this 1 minus n is between 0 to 1. That is if the n is positive and also lesser than 1, okay, and the divergent if n is lesser than or equal to 0. So next we consider so next we consider that this 1 to infinity, 1 to up to infinity, this 1 to up to so 1 to up to infinity, x to the power n minus 1 e to the power minus x dx, we see that what we can see is that so e to the power x is greater than x to the power k so x to the power k by k factorial, okay, and this is also greater than x to the power n plus 1 k factorial. So these are consequences, okay, where x is greater than 1 and k is a positive integer. So k is positive integer, so where k is positive such that this k is greater than n plus 1, we can write. Okay, so it means what? It means that this k factorial, so if I just take the k factorial of So this k factorial by over x to the power n plus 1. So this term is greater. This term is obviously greater than e to the power minus x, or you can say that e to the power minus x, x to the power n minus 1 is lesser than k factorial by x n plus 1 over x to the power n plus 1, and these things, which is e to the power minus x, x to the power n minus 1 things is lesser than k factorial by x square. So these are some consequences I am just letting you know, and helping you to understand that how this proof can be done. So these are some consequences. So it is some obvious consequences, or if you have any doubts you can prove it by mathematical inductions, I guess. So if I just take the integral, okay, so the integral of 0 to infinity, 1 to up to infinity. So the integral 1 to up to infinity, 1 to up to infinity x to the power n minus 1 to the power minus x dx, which is lesser than the 1 to up to infinity k factorial by x square dx, and this entire terms is lesser than the k factorial, okay, which is a finite number. Right. So what we can conclude that, so this integral 1 to up to infinity x to the power n minus 1 e to the power minus x dx, this is convergent for all value of n, rather square root of n, I should say, so which is convergent for all root over n. So you can verify these ones. So in this, so here in the previous things, so hence both the integrals, so this integrals is convergent and this integrals are convergent if n is positive. Hence the total given integral is convergent when n is a positive, okay. So now, so hence, so if you just don't write to the for all root over n, that also do not have any problem. So hence we can say that hence both the integrals, both integrals are convergent if n is positive. So therefore the this integral 0 to up to infinity x to the power n minus 1 e to the power minus x, okay, is convergent. So this proves, or this entire evaluations proves that the convergency of the gamma functions. So that's how you can check that whether this gamma integral is convergent or not, as it is the improper integral. Okay, now we'll come to evaluate the gamma integrals. So as you know, so we'll use another color. So so now evaluation of gamma integral. Okay, now so as per our definitions, this gamma n is written in this form: 0 to infinity x to the power n minus 1 e to the power minus x dx. So this is the setup of gamma functions, but we don't know how to solve and what will be the answer, or what we left with while solving this gamma integral. So we'll solve by applying integration by parts, and we'll keep the x to the power n minus 1 as a first function. Okay, so it will minus e to the power minus x to the power n minus 1, and the limit would be 0 to infinity, so plus n plus 1, and it would be 0 to infinity x to the power n minus 2 e to the power minus x dx. Okay, so the value of the, so this is the, that would be 0, the value is 0, and this is n minus this is n minus 1. So this is n minus 1. So we left with n minus 1 of this integral. So n minus, so it would be 0. This value is 0. Okay, so we left with n minus 1 integral 0 to infinity x to the power n minus 2 e to the power minus x dx. Okay, great. So since you can now write that, since limit of so how these things is going to be 0. So since the limit of n tends to infinity, then x to the power n minus 1 by e to the power x. So yeah, I'm going to shifting it next page. So yeah, so next page, so just rubbing it out. So next page, so we write that, so this is the, so since limit x approaches to infinity x to the power n minus 1 by e to the power x is limit of x tending to infinity, and so in denominator I am expanding this e to the power x, so x by 1 factorial and x square by twice factorial, and that's up to infinity, and this is x to the power n minus 1, which is 0. So this is how we are deriving or saying that this is equals to 0. Okay, so now so here, so then we can again write, so that is gamma of n is equals to n minus 1, and as per the gamma setup it could be written as the gamma of n minus 1. Okay, so applying this result again, so we can write that gamma of n equals to n minus 1 gamma of sorry this is n minus 2 and gamma of n minus 2. So how I'm getting this result? So this is the from the setup of, if you closely look at this setup of this gamma function, you will get you can write this as per the definition. Okay, so hence if n is positive integer, then repeating the same process again and again and again, what we will left off, we left with the gamma of n equals to n minus 1, n minus 2 dot 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 up to 3 times 2 times 1, and then this is gamma of 1, and this gamma of 1 is nothing but the 1. So but see, 0 to infinity, so gamma of 1 is 1. So how you can write it? By defining the integrals, so 0 to up to infinity. Okay, so 0 to up to infinity, this is x to the power 0 e to the power minus x dx. So this would be minus e to the power x 0 to infinity, and you'll get 1. So this is 1. So it means what? So gamma of n is n minus 1 factorial. Okay, so this is the one of the beautiful things of gamma function is that, so to generalize this integral, the relationship between the factorial with integrals, okay, the factorial functions and the integral, and how you can derive, so this is the way to derive it. Okay, so I hope you could, if it is the form of this, so I hope you would be able to solve. So if it is the form of in is the integral 0 to up to infinity and e to the power x, sorry, it is minus x to the power n dx. So it would be, I guess, yeah, this is n factorial. So how to derive it? So I am leaving this to you, so try to derive this. Okay, so this is all about the gamma functions, and so let me show you the graph of this function. So So yeah, you see, so this is the graph of these gamma functions. So basically, Euler found a continuous function of a real variable x, which reduces to x factorial, okay, when x is a positive integer. So the gamma functions can be defined in a number of ways, but it is convenient to define it is as a definite integral. So what mathematicians do? So mathematicians and the enthusiasts love this function because it generalizes the factorial. So as I was saying that this gamma integral is the relationship is between the factorial and the integral steps. Okay, so how to define how to generalize the factorial functions. Okay, so it is often used in probability and statistics, so as it shows up in a normalizing the constants of important probability distributions such as the chi-square distribution and the gamma distributions is also there. So the motivation, so what is the motivation behind the gamma function? So the motivation is, so the motivation of gamma function so the gamma function's motivation is to find, okay, to find a smooth curve that connects the points uh, that could be x and y. I'm taking, okay, x and y given by y equals to x minus 1 factorial at the positive integer value for x. So this is a very short introduction about the Eulerian integral. So moreover we'll definitely explore lots of fascinating mathematical insights and problems which is highly motivate us for core understanding of improper integrals, and we'll do more some problems which is related to this gamma functions, and we'll also discuss about beta functions here, and we'll find out the relationship between gamma functions and the beta functions. That mean, I mean the gamma integral and beta integral. So yeah, so stay tuned for the next um, upcoming problem solving sessions on gamma functions, and if it is possible I will definitely discuss the probability distributions like the Gaussian distributions setup, and we'll see how to compute the expectation, what do you mean by the expectations, and how to compute the expectation, the moment generating functions of and how to implement this gamma functions uh, in that kind of problem. So for this time being, stay tuned, stay energized, bye bye.